So this is problem number 5. So as always, to save time, and because I have a final and a project due tomorrow, so I just work out all the problems for the multiple choice problems so that you guys can see it. So each problem is going to take like 3 to 4 minutes maximum. Okay, so keep it short. All right, so problem number 5 says for the question, if the reaction at J is 15 kilonewtons, the force in member FH is closest to. Okay, so we know that this is a method of section problem, so we have to find out what the FH is right here, right? So FH. So what I do is that I cut it, okay? I cut the section and I only consider the right portion because the right portion it has uh less unknowns because I have this JY, right? Unknowns compared to this section we have by and bx. Although bx in this case will be 0, but I like to consider the right portion because it's just um, it's just less stuff that you have to um, that you have to work out with. Okay, so what I did right here is that first I consider this whole truss system, and then I take a moment about b so that I can find out what jy is. So okay, so moment about b, I also have first have this 12 negative 12, okay, which is this one negative 12 kilonewtons multiplied by 2 times 2.4 because each of these is 2.4 meter spacing. Okay, so two of that, so 2 times 2.4, and then minus this 12 right here, multiplied by 3 times 2.4. Okay, and then they're negative because I assume that counterclockwise is positive. So and these two are going in the clockwise direction, right? Okay. And then don't forget I have this JY2 and the JY, but between JY and uh, reaction B, the distance between them is 9.6. So I have this one right here. And then just solve for JY, I got 15 kilonewtons. All right. And then next thing we have to do is that I have to draw this diagram right here. Okay. So this is a section. And then I have to find out what the FFH right here is. Okay. So what I did is that I take a moment about G, okay, so that I can get rid of this 12 kilonewtons right here. All right, and then next thing what I have to do is that so from JY to G, the distance between them is 2.4, right? So JY is 15, distance between them is 2.4, and then distance between the FFH and G, which is 1.8 right here. So as you can see, so that just solve for FS. So just to solve for FFH, I get that FFH is equal to 20 kilonewtons in tangent. Okay, so this is a pretty straightforward problem. Problem number 6 says the gate AB is 8 meter wide. Determine the hydrostatic force on gate AB, and the density of the water is given as 1 megagram per meter cube. Okay, so first I draw the distributed load right here. So this triangular distributed load is correspond to this one right here, and the rectangular distributed load is correspond to this delta thing right here. All right. Okay. So as always, we know at the surface, this is the free surface, so P and W here will be 0, right? Okay. And then for the at B, so we know that the pressure is equal to rho GZ, okay? And the weight is equal to the width B multiplied by the pressure. Okay, so I work them out right here. All right, so uh, PB, so this one is the rho, so this one is the G, and this one is the Z, which is a depth 5 meter right here. So I got 49.05 kilonewtons per meter squared. And then for the WB, so this is the width. Okay, so width is 5 meter also because I'm considering this thing right here. So the width is 5, and then multiplied by the P, which is 49.05. So I got 392.4 kilonewton per meter squared. And then I consider P point A. So point A, so pressure A will be, so this one is the rho, right? This one is the G, this one is the Z. So Z right here is the 5 meter plus 4 meter, which will be 9 meter, okay? So putting in the calculator, I got PA is equal to 88.29 kilonewton per meter squared, and then WA will be equal to This one is the this one is the width, should be, which will be the because the question says gate AB is 8 meter wide. So right here is 8 meter wide. Okay, and then multiply it by the pressure at A. So PA is 88.29. So I got WA is equal to 706.32 kilonewton per meter squared. Okay, next thing what I have to do is that I have to do the F1 first, or you can do the F2 first. It doesn't matter. So I'll do the F1 first. So F1 is a triangular distributed load. We know that the area for a triangular distributed load is 1/2 of um, the length times the height, right? Okay, so I did 1/2 of that 706.32 because that's the higher value. Subtract 392.4 because that's all we have to get right here. Okay. All right, and then multiply by the by this thing right here. By the hypotenuse, which I can get it. I can obtain that by doing the Pythagorean theorem. Okay, and then again, my F1 is equal to 784.8 kilonewtons. Okay, and then for my F2, F2 is easy because F2 is a rectangular distributed load. So all I have to do is simply take that 392.4 and multiply it by the height, 5 meter. So I got F2 is equal to 1962 kilonewtons. And then to find out the hydrostatic force, that's basically just the FR. So I just take F1 plus F2. So I got my FR is equal to 2746.8 kilonewtons. Okay. Problem number 7 says determine the surface area and the volume of the solid formed by revolving the shaded area 360 about the z-axis. Okay, so this question is very similar to one of the problem that we did in the SI 17, where we have to find out determine the surface area and the volume of the solid revolving about a specific axis. Okay, so first let's do the area first. So the area equation we know is equal to 2 pi y bar multiplied by the length. The y bar, we know that that's just the centroid of that segment, right? Okay, so first I label that point 1 is right here, okay? So A1 will be equal to 2 pi, and then the y bar for that is simply just 15 divided by 2, right? Because point 1 is located half distance between, is located halfway in that 15 inches, so 15 divided by 2, and then the length of that is simply just 15, right? Because it's along this thing right here, okay? And then A2, I consider A2 is right here, okay? Because I'm doing the area, so I have to consider every edge, okay? I have to consider every, what's that word? Like the parameters, okay? So that's why I have to consider this point, this point, this point, and this point, okay? Because that's basically what we have to do when we do the areas, okay? We don't consider this point right here because at this point, we don't have any y bars, okay? So that's why we don't consider this point right here. We only consider its outer edge parameters. Okay, so A2 is right here. And then we know that the centroid for the A2 is basically just 15 inches, right? And then the length will simply be that 18 inch. So that's what I got for A2. And the A3 is 2 pi multiplied by, so it will be that 15 right here, okay? Plus this 15 divided by 2, because we know that the length for this bottom, but this bottom length is 30 inches, right? So and then the top one is 15. So which means that this point and this point will be 15 inches too, right? And then we know that when we do the um, centroid for 3, so centroid for 3 uh, is right here, right? So that would be simply be that 15 plus the 15 divided by 2. So that's what I got right here. So that's the y bar. And then and then excuse me. 25 right here. What I did is that if I consider this triangle right here, okay, so know that this one's 15, right? And this one is 20, okay? So by Pythagorean theorem, we know that this hypotenuse right here will be 25, okay? And that's the length of point AD right here. So that's how I got 25. And then for the A4, which is the bottom one right here, it'll be 2 pi multiplied by the century, which century will be 30 divided by 2, and then multiply by the length, which would be 30, okay? And then just basically sum all A1 to A4, and I get my A, which the area is equal to 8765.04 inches squared, okay? So that's what I found for area. And then for the volume, I only have to consider two segments right here, which just the segment one and segment two, which has segment one is the rectangle and the segment two is the triangle. Okay, and then we know that the equation for the volume is 2 pi y bar multiplied by the area, right? And that area is the area of that segment. It's not the area for the entire composite body right here. Okay, so my V1, which will be 2 pi, and then the century will be 15 divided by 2, which is our y bar, and then multiplied by 38. Mistake right here. It should be 15 multiplied by 38, because we're considering the area. So 15 multiplied by 38. So that's the area of the V1 right here. And then for the V2, which will be 2 pi plus, because this is the axis, right? This is the Z axis. Okay, so the V2, for that y bar, we have to consider from the origin to the century, which is at this point right here. So which will be that 15 plus 1/3 of 15 uh, 15 inches. Okay, so that will be the y bar. And then for the area, the area for the triangle is 1/2 base times the height, which would be base, which would be the 15, and then the height right here, which is the 20 inches. Okay, so I got my V total volume will be 45,710.17 inch cube. Okay, so that's what I have for this question right here. And for problem number 8, it says the 4-meter wide open tank is hinged at its bottom A and is held in place by a thin rod BC. The tank is filled with glycerin, whose density is 1263 kilogram per meter cube. After the tank is filled to a depth of 2.9 meter, the force T in the rod is closest to. Okay, so what we have to find out is this T right here. Okay, so same equation, P is equal to rho gz and W is equal to the width B multiplied by the pressure P. Okay, so at B, we know that that is above the water surface, which means that it doesn't have any water pressure and doesn't have any water weight. Okay, so we only consider this point A right here. So point A, so I got this one is my rho, so G, and the depth is given, which is 2.9. Okay, because the total depth from P to A is 3 meter, but the depth that's on, but the water depth is only 2.9 meter. Okay, so that's how I got my TA pressure at A is equal to 3593. I mean, 35,931.8, my bad, 35931 newtons. And then WA will be the width, which is 4 meter wide, because it says 4 meter wide open tank. So 4 multiplied by 35931. So I got 143724 newtons for WA. And then I can find what my P is. Okay, so P, I know that this is a triangle distributed, so my P will be the 1/2 of the WA multiplied by the depth 2.9. So I got my P is equal to 2083.99.8 newtons. Okay, so next thing I have to do right here is just take a moment. Okay, so I take a moment about point A because I find out what my P is. So if I take a moment about point A, so I can find out what my P is. Okay, so this is my P, and then we know that this since it is triangular, this should be low. So this one will be half of the distance right here. I mean, my bad, not half, 1/3 of the distance from P to A. Okay, so that will be 1/3 of multiplied by 3, and then plus T multiplied by 3 because the distance between perpendicular distance between T to A is 3 meter, right? Okay, so I got my T is equal to 69466.6 newtons, or you can write in Q newtons, which will be much easier to write. So it will be 69.4666 Q newtons. Okay, so guys, I want you guys to remember this question, and because this is a kind of fluid question that he might put on the exam, and also like this kind of question, because these are kind of fluid question that he will normally just put on the exam. And other than that, like remember this friction problems, okay? And also this one right here. I want you guys to remember how to do these, okay? Because these questions, like problem 1, 2, 3, 4, 5, and 8 are all come from the previous semester's exams. Okay, so these are, I mean, so this is like level of difficulties of the finals. Okay, all right, so guys, just uh, just relax and study hard for the finals, and I wish you guys good luck and I'll make an A on the finals. Okay. All right, thank you guys so much for this semester, and please fill out the end of the semester's SI evaluation. I'd be greatly appreciated. All right, thank you guys.